Welcome to the lecture on gating system design. In this lecture, we are going to discuss about the pouring time calculation results. So, as we have discussed that the purpose of gating system is to ensure that the liquid metal, once it is poured, it should move in the gating system, and in an optimum manner it should fill the cavity without minimum of turbulence, minimum of time taken also, because as the time taken will be more, it will try to basically be colder and colder. So, there may be defects related to that, and as the molten metal is flowing, so there are certain principles which are applied, and these principles are basically related to the fluid flow, because it is a fluid which is flowing. So, normal fluid flow principles apply in that. So, principles of fluid flow for vertical and horizontal passages are used for calculating the pouring time of casting, as well as it will give you the advance warning for any undesirable turbulence and aspiration of mold gases. So, this is what is important to understand in case of gating system, that what are the basic principles, and because when we discuss about the gating system, the challenges which remain are in case of permeable molds. If you have the permeable mold and if the channel is not running full, in that case, if during the passage somewhere the channel is not running full, and if there is a condition generated where the pressure is less than the atmosphere, then in that channel the atmospheric gases may enter, and that may spoil the quality of cast, particularly if the cast metal is prone to getting oxidized or it is a drossy material. So, that is how, I mean, that can be understood by reviewing the formulations for this fluid flow, where you have the basically you have two basic principle is there, two important principle are there which are used, that is related to fluid flow. One is the law of continuity. So, as we know that the law of continuity tells that the mass is conserved. So, when you have any channel, so at 2 points the conservation of mass should be applicable. So, conservation of this mass is nothing but rho 1 A1 V1 is rho 2 A2 V2. So, that is how this law of continuity holds good. So, in that, if the rho is basically rho is the density of fluid, A is the area of cross section of the channel, and V1 V is the velocity. So, if you have 2 points, so if you have 2 points, then at 1 and 2, so if the area is same, if it is area is A2 and this area is A1, then A1 V1, so this is V1 and this is V2. So, A1 V1 will be A2 V2. So, this is for incompressible fluid, where the fluid is incompressible, fluid is its density is same. In that case, this law of continuity is applied. So, that is one law of continuity. Now, next is the Bernoulli's equation, which is nothing but the conservation of energy equation. So, Bernoulli's equation is used because in this case the fluid is passing from the pouring basin coming to sprue well, then it is moving from there to the runner, and then it is going to enter into the cavity through in gates. So, this is basically there are different heights, the potential head is decreasing. So, in the Bernoulli's equation what we see that normally energy will be constant. So, that is what the sum of the heads of the energies, you have 3 kind of energy which is taken. One is potential energy term, then you have the kinetic energy term, then you have the pressure term. pressure energy term. So, basically what we see is that at these two places, if you try to see the Bernoulli's equation, it tells that this energy will be basically constant. So, what that tells? That tells that P1 by rho plus V1 square by 2g plus H1, it will be P2 by rho plus V2 square by 2g plus H2. So, that is what normally if you have 2 points, then in that case the energy, this term has to be same. That is what the Bernoulli's equation tells. Now, in this case basically you may have the loss term. You may have the loss term in between, because once it is coming from 1 to 2, there may be losses from 1 to 2. So, this loss will be energy loss 1 to 2. But then if we neglect it, then in that case, because this loss will be based on, so because it is passing through this path, so this surface is not smooth, you will have the friction forces acting, you will have viscosity, because of that there will be losses. So, this loss comes into picture, but then if we neglect them, in that case if we neglect it, you will have this simplified expression that tells that how to find the velocity at different positions. If suppose you take this position, in that case what we see is that if you look at these two places, if you have a container here, and then if this is full of water and this is 1 and this is 2. So, if from here this is water is flowing out. So, in that case, and if this height is h, so you can use the Bernoulli's theorem, and in that case this rule will, this expression will be valid. Now, in this case, this 1 is also open to atmosphere, and 2 from here also it is going into atmosphere. So, P1 and P2, they are open to atmosphere. So, that is basically atmospheric pressure, if you assume, because if it is open to atmosphere, you have 1 atmospheric pressure. Now, here the fluid which is there, this will be basically 0. So, V1 is 0. Similarly, you have, this is as you can say H1. So, if this is, so H2 will be 0. So, you will have H2 as 0, because this is a datum line. So, you can take the H as 0. So, you will have H2 as 0. So, you will have this 0, you will have this 0, this and this is cancelled. So, what we see is, you say that you say V2 is root 2g and then H1. So, using the Bernoulli's equation, you can see that when a liquid will be falling from a height of h or height h1 say, or whatever it be, in that case the velocity which is attained when it is coming out of the orifice or nozzle, in the case of casting you will have here the sprue well or the level of the gate from where the metal will enter into the cavity. If it is having a potential head, this head is about h1 or ht, total head is ht. In that case the velocity which you get, it will be under root 2g into height, that is head height. So, this is how this Bernoulli's equation is used for finding. So, this Bernoulli's equation basically this is applied at different places, and then you can get certain conditions by which you can come to some cases, like when we talk about the casting and in the cavity, basically you will have the probability of having certain aspiration. So, we will discuss about the aspiration effect, how this aspiration effect comes into picture. Let us say you have pouring basin, and this is of height is this is height is hc, and this is height is ht. So, in this what happens in the case of pouring basin, the liquid metal will be here, and then from there it will come through this sprue. This is the vertical sprue, and the liquid metal will be coming through this, and it is coming to this lower portion. Now, let us, if this is the total height of HT and this is HC. Now, if you have the point as 1, this is the point 2 and this is point 3. Now, what happens that if you you have to apply this Bernoulli's theorem between the points. So, suppose you apply this Bernoulli's theorem between point 1 and 3. So, between point 1 and 3. Now, if you apply that, so you will have P1 plus V1 square by 2G plus H1. So, H1 is nothing but HT, and that will be equal to P3. So, P3 by P1 by rho, P3 by rho plus V2 square by 2G plus H3. So, that is 0. Now, since this is open to atmosphere and this is also open to atmosphere from where the liquid metal is flowing, so this is also cancelled. Now, you will have V1 as 0. So, as V1 is 0 because it is at the top surface, the velocity is 0. So, you will have V2 as root 2G HT. This is by the simple application of this by applying the Bernoulli's theorem in between point 1 and 3. Now, again if you apply the Bernoulli's equation between point 2 and 3. So, applying Bernoulli's equation between point 2 and 3. So, what we get? We get P2 by rho plus V2 square by 2G plus you will have this height. So, this height will be H2 suppose, then it will be equal to P3 by rho plus V3 square by 2G plus basically you will have the last term is height. So, this height is H3, that is 0. Now, the thing is that if you apply the continuity equation between these two points. Now, applying the continuity equation tells that A1 B1 will be A2 E2. So, since the cross section area at these two places are same, at point 2 and 3 the cross section area is same. So, using the continuity equation, in that case your area at this place and this place being same, velocity will be same. So, if you apply the, so using continuity equation, V2 has to be equal to V3 as you have A2 as equal to A3. So, once V2 becomes V3, in that case what you see is you will have P2 by rho, it will be equal to P3 by rho minus V2 square. So, this minus H2. So, P2 will be equal to P3 minus H2 rho. So, that is what we get here. So, this will tell you the result as P2 equal to P3 minus rho H2. Now, what it tells? This tells that if you are putting this channel straight, in that case at this point P2 the pressure will be less than P3 by this quantity, and P3 is the atmospheric pressure. So, P3 being the atmospheric pressure, at this point the pressure becomes less than the atmospheric pressure, means the vacuum is generated, and if the pressure is less here than atmospheric pressure, in that case if the mold is permeable, then it will try to maintain the atmospheric pressure here, and in that case it will suck the atmospheric air or gases from this side through the permeable mold. So, this sucking of air or gases because of the pressure difference created at this place, that is known as aspiration, and this aspiration is not good in the sense that if the material is prone to oxidation, in that case that material get oxidized, it may get impure. So, this aspiration needs to be minimized. So, the aspiration needs to be prevented. Now, how to prevent this aspiration? This aspiration is prevented by the use of taper, and we will see that how this taper has to be done by so that there is no aspiration. So, basically what happens for preventing this aspiration, what we need is this pressure should be equal to this pressure. So, that is when the aspiration will not take place. So, that we have to see. So, we have to see that how this aspiration can be prevented. So, for that again we will see that you have the pouring basin of, and the HC is the height of the cup, H2 is the height from here to, H2 is the sprue height basically. So, here also this is the height H2 basically, that we have already taken this height as H2. Then you have total height as HT. Now, in this case if we apply the equation between point 2 and 3, so in that case, so what we see that we will assume a case where there is no aspiration. Now, there is no aspiration means what? The pressure, so if this is 0.1, if this is 0.2 and if this is 0.3. So, in the case of no aspiration, so this is for prevention of aspiration. Actually, aspiration occurs only because there is less pressure here than atmosphere, which is the pressure which is here. So, for prevention of aspiration, you have to have P2 as P3. So, what we see is we have to again take the equation this. Now, in that you get again P2 plus V2 square by 2g, P2 by rho plus V2 square by 2g plus H2 will be P3 by rho plus V3 square by 2g plus H3. Now, as we discussed that P2 will be P3, so this term will vanish, because we are thinking of no basically aspiration. H3 will be 0 because it is the datum line. So, S3 will be 0. Now, V3 is nothing but root 2g HT. So, you will have the V3 term, V3 because it is the height of the total height basically. So, as we have understood by using the applying the Bernoulli theorem, you can have the expression for V3 square by 2g. This V3 square by 2g comes as V2 square by 2g plus H2. This is what we get when we apply this Bernoulli's equation between 2 and 3. Now, if the area here is A2, then in that case using continuity equation we get A2 V2 as A3 V3. So, what we see is we can write V2 as A3 by A2 into V3, and if this A3 by A2 is taken as a ratio, this ratio is defined as R into V3. So, this ratio, because this is the ratio of the area of cross section at this point and this point. So, if you put this V2 term into this expression, so substituting this value of V2 into this equation, what we get is V3 square by 2g will be V2 square by 2g means R into V3. So, this is R square V3 square by 2g and plus H2. So, now V3 is 2g Ht. So, we know that V3 is root 2g Ht. This is H subscript T. So, V3 square will be 2g Ht. Now, what we see from here that V3 square is 2g Ht. So, 2g Ht by 2g minus R square into 2g Ht upon 2g, it will be equal to H2. So, you will be having these terms cut. Ht into 1 minus R square will be H2. So, 1 minus R square will be H2 by Ht. R square will be 1 minus H2 by Ht, that is Ht minus H2 by Ht, and this is equal to H2 Ht minus H2, this is Ht and this is H2. So, this is Hc. So, this is Hc by Ht. So, this R is coming as under root Hc upon Ht, H subscript C upon H subscript T. This is the condition which should be followed for the prevention of aspiration. So, this is what the condition which must be followed, so that there is no aspiration in the gating system. So, we are going to discuss now about the time of pouring. Now, how to find the time of pouring? So, as it is very simple in case of top pouring, because in case of top pouring what happens that you have the mold cavity and you will have the sprue coming up, and this may go from the side or it may go from the top. So, you know the head, if you know the head, this head, if you know this head, now you can find the velocity here. So, in the case of top pouring, simply if you know this total head available, this head does not, if it does not change, in that case if you have the pouring basin here and pouring basin maintains the fluid level at certain value, in that case this head will not change. So, the velocity which will be achieved is under root 2g h, if h is the total head available while it is entering inside the mold. So, in the case of top getting, it is coming from this place or it may be from this place. And once you know this velocity, then if you know the AG is the area of cross section of the gate. So, here the area, if it is AG, in that case AG into V, that is AG into root 2 GH. So, this will be volumetric flow rate. So, this will be volumetric flow rate. So, in that case the pouring time calculation will be calculated by dividing this volume of the casting divided by this volumetric flow rate. So, this is very simple in the case of the top pouring cases. Now, what happens in the case of bottom pouring? Now, in the bottom pouring cases, if you have the situation like this. So, this is suppose here in the bottom case, bottom pouring, suppose this is the total head available as HT and this is the height of the mold HM. This is the mold, this cavity, this is the height of the total height, that is here you have pouring basin and this is your sprue and then this is the datum line suppose. Now, in this case what happens that the head available, the head which is available here, this head is basically changing. Initially when it starts going inside the cavity, at that time you have head available as HT. So, initially the velocity which you get here, that will be under root 2 G HT. However, with time when the height changes, so if suppose it comes to height h at in time dt, if suppose it has achieved height h in time dt, now at that particular time the available head is st minus h. So, velocity will be under root 2 G ht minus h. So, because this liquid level is decreasing and at this point when it is filling, at that time effectively the head available is ht minus hm. So, the height, I mean the velocity using the Bernoulli's equation can be calculated as under root 2 G ht minus hm. Now, if suppose here the area is AG and if area of the mold AM, that is cross sectional area of mold. Now, what happens in this case, if suppose in the time dt it has come to dh height. So, you assume, so now we are going to have the case for bottom pouring, okay, and if during time dt the level of metal reached in mold is H. Now, this will be basically at that time the area is AG and the velocity which is here, this velocity will be basically, so what we see is the velocity will be root 2 G and ht minus h. So, that will be the velocity and velocity into area of the gate. This will be the basically this will be the basically volumetric flow rate. This is area of the gate and this is the volume, this is a velocity at which it is flowing through that. Now, this will be nothing but you will have the volume multiplied. So, that will be, now it will be equal to V. So, this is the area AM. So, that will be AM into the height h. Actually, we will take this height. So, during the time dt, this height should be dh. So, this will be dh basically. At particular instant the height is h. So, during the time dt, the height achieved is dh. At a particular instant this height is h. So, it will be dh, and this is achieved in time dt. So, you will multiply this with dt. Now, this is the equation which you get. This equation needs to be integrated. Now, this dt once integrated will give you the total time taken, and this dh will be from 0 to hm. So, you bring the so dt, integral dt will be am upon ag into dh upon root 2g ht minus h. This is what you get, and once you integrate, so this will be also integrated. Now, this dh will be integrated. So, dh will be varying from 0 to hm. So, from here you get am upon ag, and then this root 2g will come out, and once you integrate, so this will go from 0 to hm. So, that will be 1 by root under root st minus h. So, it is basically 2 into under root ht minus h, and then it will be again minus, because this is minus h. So, once you are integrating, this minus sign will come, and you are putting the values from 0 to hm. So, this is how you are basically finding the value. So, it will come as am by ag root 2g, and then first of all you will put hm. So, it will be st minus hm, and since it is minus, so this is 2 is coming here, and then so first term will be root ht minus under root ht minus hm. Now, this is the expression 2 ag upon 2 into this is am. Two into am upon ag into under root 2g, and then in bracket under root ht minus under root st minus hm. So, this is the pouring time calculated for this bottom pouring system. So, whenever you are given the bottom pouring system, in that case you will have to see, now you suppose this mold height is such that it is coming up to this place. So, in that case this term will vanish. Okay. So, this way you can calculate the pouring time. Now, depending upon the this height, this term will be changing. You have ht as fixed. So, this is how you can calculate the pouring time for basically the bottom pouring cases. Thank you very much.